So I'm Dr. John Warner. I'm the Chief Customer Officer here at American Battery Solutions. I helped found the company back 6 years ago now, and I've been in the battery industry for about 15 years. And then I spent about 20 years in the auto industry out of that. So I like to think that I combine the best of the automotive and the OEMs with the battery technology world. And I am a true battery guru. Well, I will say maybe a geek rather than a guru. There's a lot of people out there smarter than me, but I really enjoy the batteries, the battery technology, and I love what we do here. So first of all, batteries have been around for a very long time, and we can talk a little bit about battery histories. But batteries and modern battery technology, even the modern EVs, they go all the way back to 1890s. We were using nickel metal hydride in about 1981. We were using nickel iron and nickel zinc and lead acid batteries back 100 years ago. About the early 1970s, you had some really awesome innovations by three guys in particular who've been highlighted by the industry. Stan Whittingham, Dr. Stan Whittingham, who is a great member of our industry trade group, NatBat, and a good friend of ours. Was one of the first inventors and did some of the first discoveries of lithium-ion back in about 1970 and 1971.
And then that work continued to progress, and in the early 1980s, both John Goodenough and Akira Yoshino made additional discoveries around lithium-ion batteries.
And all of that led to the commercialization of lithium-ion batteries in 1991. And that was when we saw Sony introducing the first 18650s with an LCO chemistry way back in that. And that was about 80 watt-hours per kilogram. So that was twice what you were seeing with any nickel-based battery, 3 times more than you were seeing with lead. So it was a great improvement. And that technology is what enabled all of the things that we've got today. That enabled our cell phones. It enabled us to have laptop computers that we could take with us. That innovation allowed us to unplug from the wall. And that continued to evolve. And in the 30 years since that technology really evolved, we've got to the point where we're seeing production lithium-ion cells sitting at 280, almost 300 watt-hours per kilogram today. So energy density has gone just through the roof, and it continues to drive up as new technologies speed into them. But it's enabled all the things that we do today, like electric cars, electric transit buses, and all of the e-bikes and everything else that we see in the world. All the mobility applications are starting to implement some form of electrification, and it's all managed and it's led by the lithium-ion technology.
Awesome. So building off of that, what are some of the key innovations and breakthroughs during the early days of lithium-ion battery development?
Well, lithium-ion is interesting because it's all about the chemistry, right? So whereas a fuel tank, you're just physically storing gasoline, when we're talking about batteries, you're always talking about this chemical reaction that needs to happen. And so what we saw is an evolution of chemistries. The first Sony cells used a lithium cobalt oxide chemistry. Some of the work that Goodenough did back in the 1980s led to the innovation of lithium iron phosphate, which drove the energy density up, and it reduced some of the cost and gave some better technologies. We saw that evolve into a nickel manganese cobalt. We saw lithium manganese oxide. So we saw this kind of evolution of chemistries. When we think of the word lithium-ion, I always think of it as an umbrella term that really covers a lot of different chemistries. Think of it like making a cake. You said you're going to make a cake, that's the umbrella term. You're going to make a chocolate cake is a specific recipe you're going to use. Lithium-ion really falls in that same way. So there's all kinds of different chemistries. And it's all been enabled by the cathode materials, the anode materials, the separators, and the electrolytes. Those are the 4 key components which drive the technology within the cells from their introduction until today.
Awesome. I really like that analogy. So next, in your book, The Handbook of Lithium-Ion Battery Pack Design, you discuss various battery chemistries, and can you elaborate on the significance of these different chemistries?
Yeah, absolutely. So we just launched the 2nd edition of the handbook. The handbook is a really great tool for anybody trying to learn batteries. I lovingly refer to it as what do I wish I knew when I started in the battery industry. Really intended for anybody that's coming into the battery industry to get a feel for what's going on in there. It's not going to make you a battery engineer, but it's going to allow you to understand the technologies. And what we talked about in the latest edition is we really expanded on the growth of those lithium-ion chemistries. So we're seeing an evolution. We're always looking for the next stair-step technology, but you're seeing huge evolutions in current gen technologies. For instance, In the NMC, nickel, manganese, cobalt family, we've now seen NMCA, where we've had aluminum getting added to that. Some of the major manufacturers are already using that brand of chemistry. We've seen other manufacturers now starting to try to eliminate the cobalt. Cobalt is very expensive. It's the most expensive raw material we use in the cells. So if you can reduce the amount of cobalt in there, then you can reduce the cost of the cell. So you're seeing NMX, nickel, manganese, and no cobalt. Then you're seeing the NMCs traditionally starting to move away from the traditional 1-1-1s, where you're looking at the ratio of 33% nickel, 33% manganese, and 33% cobalt, all the way up to 0.5, 0.5. So 90% nickel and a 0.5%, 5% cobalt, 5% manganese. So you're really trying to see that evolution of those. Even on the LFP chemistry side, we've seen this evolution with lithium manganese iron phosphate. So this drives the energy density of the cell up significantly, but it retains some of the performance from a power and a cycle life standpoint that you're seeing. And then, of course, if we look out into the future, there's some great work happening right now, and we're already seeing some of the next generation technologies starting to emerge into the market. Sodium-ion is starting to find a place. There's already several manufacturers in production today. Solid-state batteries and semi-solid-state batteries are beginning to emerge right now. We've got companies that are launching them in small applications today and looking to increase and grow those into more mobility-based or automotive applications in the next 4 to 5 years.
Very interesting. So now expanding on that, how have advances in lithium-ion battery technology addressed the challenges of energy density, safety, and cost over time?
Yeah. So that's a really good question. Safety is one of the key, and I think it's the key aspect of any battery, because if we can't make a battery safe, then it doesn't matter what it costs, or it doesn't matter how much performance it gets or how much cycle life. So there's a lot of great work going on by many companies looking at all kinds of different solutions. Lithium iron phosphate is generally considered a safe chemistry. I think of it as a more abuse-tolerant chemistry. We can still drive it into a thermal runaway, but it is more acceptance of abusive conditions than some of the NMCs or NCAs. We've also got great companies out there like Soteria Battery Innovation Group, but ABS is a member of their consortium, who are working on new emerging technologies to help improve the safety of those batteries. So one of the things that Soteria is working on is taking your traditional foils. When I create a lithium-ion cell, you're taking an aluminum foil and a copper foil, and I'm coating my active material on those. And what they've developed is they've developed a process that rather than using a solid piece of aluminum for that foil, they're metallizing a piece of plastic film. What that does is it reduces the weight of that film by about 75% and the cost. It also increases the safety, so that if you were to have some debris in there or do a nail penetration, that plastic melts away around that spot and it acts as a fuse at the electrode level, driving the safety up significantly in those solutions. And then as we look at future technology, we talk about cost. As you drive energy density up, your cost per kilowatt hour comes down. So the more energy you can get into it, generally the lower the cost per kilowatt hour. So as we start to see solid-state batteries emerging, they are still expensive today, but as they start to go through the cost reduction curve that lithium-ion mainstream batteries have, you'll see their cost per kilowatt hour coming down very significantly. So we've seen costs go, and I'll just give you an example from about 2009, 2010, when the first Nissan Leaf, Chevy Volt, and the Tesla Roadster launched. Battery prices were over $1,000 a kilowatt hour. We're sitting here today with automotive prices about $115 to $125 a kilowatt hour. Commercial vehicles and other things a little bit higher just because of the lower volumes. And if we look into China, we're seeing prices below $100 a kilowatt hour. So we've seen a 90% reduction in costs in the 10 years. While solid state are expensive today, they will follow a similar curve over the years as the volumes start to increase.
Awesome. Final question here. How has the role of battery technology shifted with the rise of electric vehicles and renewable energy storage?
Yeah, so that's a great question. And I would say that, as you start looking at specific applications, you're driving innovations in technology. We've seen that whole umbrella of lithium-ion chemistries getting used across very different applications. So, for instance, we look at a lithium titanate oxide, or LTO chemistry. It's a low energy density solution, but it is a very high power and a very high cycle life solution. So we've got applications in the mining industry, for instance, where we're doing above ground mining trucks that need high power, 5C, 6C discharge. But they need to run all day long, and they need to fast charge all day long. So they're going to need tens of thousands of cycles. We can do that with the LTO chemistry. We can't necessarily do it with an NMC chemistry, or not as easily with an NMC. You would have to oversell. So we see the different chemistries kind of finding different niches in the market where they play. I think you will see the automotive industry, splitting into 2 or 3 different chemistries. I think your high-range, long-range premium vehicles will end up with NMC's NCA-based chemistries. Your more mainstream mass-market vehicles probably with LFP or LMFP. And then you may even see the sodium-ion taking up some of the city cars in places like China, where you've got less than 100-mile range and very, very small cars are needed. So I think as the market evolves, you will see different chemistries fitting into different niches within that market.
Great. Well, thank you so much. Before we wrap up, is there anything that you'd like to shout out or make any comments on?
No, I just thank you for the time, for being able to talk here. You can come and see American Battery Solutions, and you can see me speak at all kinds of different events. So come and see us some of these events. We'd love to talk to you there.
Awesome. Thanks so much for your time.
Thanks. Thank you.